So for our next talk, we have the AMD backend bringing Triton to AMD GPUs. Again, I'll get the presentation set up and we can get started.
Do we both mics? So yeah, we're both. Test. Okay. No, back and forth. Is there a clicker? Hey everybody, Lixun and I from AMD. We're going to talk about how we brought Triton to AMD GPUs over the past 6 to 12 months. I'll just get to the next chart here. Oops. There we go. Okay. So yeah, so we've been working on this for about a year. We originally started looking at Triton. It was a dependency of deep speed. Deep speed is important to us and it's important to our customers. It really kind of kicked into another gear once PyTorch 2 picked it up, right? So we spent a lot of work on it. So this is just a quick update of where the backend is, and then I'll kind of take you through the story of what all we did to bring it. But so the code is out there. So we have the third-party PR 1983 there was merged. So we have our third-party submodule link in the OpenAI Triton repository now, which is great. So you can. I have another slide on this on how to check it out, but it's all in there. The actual development happens in our repository though, so the submodules will link to our ROCm software platform Triton to a specific commit level there. So yeah, so that's the development. I have another chart on that in a minute. I'll talk about it. So hardware support, we focus on our CDNN GPUs, which are big data center ones. We do have experimental support for the RDNA as well. So that they both should work. There's different warp sizes on both of those. So we have auto detection for the hardware implemented in there now. So we Triton is able to find out what hardware we're on and do the proper thing there. But CDNA is our lead development platform on there. We do have full support on PyTorch 2 for all the ops that are lowered to Triton. We're working on the PyTorch 2.1 at the moment, so all that works at the moment, which is great. We did add. We didn't have to change much of the front end, like almost at all, right? But we did add this device type of HIP if you're calling directly into the compile, and you wanted to specifically call out the device as a HIP. So, okay, so scoping the port. Beyond the needs of dependencies, right, for deep speed or even PyTorch, right? We had to kind of see does this map well to our hardware, right? Is this worth doing? And the answer is absolutely yes. And while I was building this chart, I was looking for some supporting evidence of this, and I didn't have to look far. Phil's original paper and even the docs directory out in the GitHub Triton. GitHub out there is a good source of information on just kind of how things map over, right? So the original design tenets of kernel level blocks and locality and efficiency and high occupancy all just translate really well to AMD GPUs. So that was just green light. Let's go ahead and get this optimized and working on our hardware. But beyond that, beyond the design though, what are the pieces here, right? What is there something here that's gonna take a long time to port? What are we gonna do? Well, so we had to go through and look at everything. So first and foremost, LLVM, MLIR, those are big pieces, right? We have AMD's already made huge investments there, obviously, right? Our ROCm toolchain is LVM based. We have our ROC DL dialect and MLIR. We've already been there. We've already enabled all that. It works really great. We use that in all sorts of different places today. So, so beyond that, like, so what's higher up? The Triton GPU dialect does have some NVIDIA specifics in there, but while we were looking through this and porting it, we didn't have to really even touch that very much. So we didn't have to add any new ops. All the ops just kind of work the same way as they do on NVIDIA. Lowering the dot op is a little bit different because we have our matrix cores versus the tensor cores. So that there's another topic on that. I'll save that for a minute. But even at that layer, we were looking pretty good. So beyond that, and then we've got all the different layouts, right? So our shared memory on AMD GPUs is the design is very similar to the NVIDIA design. So all that, the shared memory layout mostly just kind of worked for us as well. We do have different sizes of shared memory. On ours, we have slightly less shared memory, but we have more general purpose registers. So at this point, it came down to more of a tuning thing, right? We want to prioritize maybe our general purpose registers more than, and try to be more conservative on the usage of the shared memory, and that is evident on some of the pipelining passes that we're talking a little bit about today already. So and we'll talk about a little bit more of that in a second. So and then the other thing then is the inline PTX, right? So we don't have PTX, so we had to so the PTX builder was resident. We had to build a GCN builder. So we've got our GCN builder that would just build inline assembly for our AMD GCN assembly. So that was one piece we did have to go and change. But all this was to map towards our the current hardware that we've got on the bottom there. Those are the specs. So it all looked pretty good. So we had to come up with a plan on getting all this working. And then see if there's anything else that we were missing that we need to work on. So the first thing was, let's get our empty kernel working, right? This was just kind of the bulldozing effort to get everything. Just we can get all the we had to, that's not a big deal. We could parameterize that. We've got we implemented parameterize, and we call it the AMD terminology is wavefront. So wavefront warp size is interchangeable. So we've got that plumbed in, and we can have auto detection. So on our RDNNs we have 32, on the CDNN we have 64. And then the kernel launcher code, we had to build new template code for the kernel launcher. And then that was pretty much it we needed to do for the empty kernel. We were off and running. Get all the ops working, and this was where we need to get that GCN builder in. There's a couple other things that we had to work out. Some of we had to disable the existing pipelining paths, for example. And then so that was probably one of the larger efforts, just kind of getting through all that, right? So we've got the plumbing in, we've got all the ops working. All the tests working. We had to do .op via just kind of vector FMAs originally. So once we had all that function working, we got to let's make this thing faster, right? Let's implement our matrix cores within Triton. And so Lixun talk about that in just a minute, but we had to, Triton has the MMA layout, which is a big important piece in getting performance, right? So we initially we were kind of editing that. We ended up having an alternate layout, the MFMA layout. Our instructions are MFMA instructions. So so that just kind of slots alongside the MMA V2 and V1 and V2 and now V3. So we'll have MFMA layout as well. So that that brought us up to speed on our matrix core support and the original, or the and then which had our flash detention working well now, and so we started doing more performance tuning and more optimization, which leads us where we're at right now, which is trying to maximize our occupancy, trying to maximize our performance, and seeing what all we can do to really kind of just tune this all the way up for our existing hardware. And Lixun would talk more about that in a little bit as well, but this mostly has a new pipelining. We're doing a streaming pipelining, which is easier on our shared memory amounts. And then we also have the swizzling, which the swizzling algorithms mostly we can reuse, but the instructions are different. So we've got that in, and we also have a piece where we can edit the number of wavefronts per EU, so we can maximize our occupancy on the hardware. Okay, so before I turn over to Lixun with some more details, I want to talk about a little bit about the third-party backend that I mentioned at the beginning. So this is merged now. There's the commit here where we're pinned to at the moment. This does predate some of the performance stuff we'll be talking about today, but we're working on a synchronization effort that brings in a lot of the commits that were committed upstream the past month, right? That all the Hopper stuff. So there's so much new code there. We're taking a little bit. It broke some of our stuff, so we're working through that. So once we get that all synchronized up, we're gonna update that commit, and then we'll have kind of everything on the top layer and have that commit from the front end be the fastest one that we've got. So look forward to that. So there's also on this chart on how to build it, right? So there's a environment variable we use, Triton, CodeGen, AMD HIP. And then you can just check out recursive and then build like normal, and then you'll get the AMD backend enabled for that. It's pretty cool. And thanks to the Intel folks, this was kind of a collaborative effort between everybody to try and let's get layer. So we've got and it's the same for us too. We've got the Triton GPU ROCm, and there's a lot of duplicate code there. So we'll have to work together to try and reduce that duplication as we go forward. So, okay, let's go over to Lixun. He's going to go through some of the more lower level details on the port.
Okay, so can you hear me? Good. No? No. What about now?
What is this one?
Good. Sorry. Does it not work?
Hello, this is working, right?
Okay. Let's talk about optimizations we have done on the AMD GPU, the MI series. Give me a second, please. Okay, cool. So, okay. So first, let's talk about the AMD matrix cores, which is a counterpart of NVIDIA's Tensor cores. And it supports a full range of mixed precision jam operations, which is achieved by variations of MFMA instructions. So this is okay. So the key to harnessing the MFMA instruction is its data layout, which refers to the distribution of elements among threads in the warp. So this is an example of data layout for MFMA 32 by 32 by 8 flow 16 instruction. So as you can see, so in general, each thread is assigned a segment for elements. And for input A, the elements in the same segment is in the same row, and consecutive threads are assigned segments along the M dimension. For input B and output D, elements in the same segment are in the same column, and the consecutive threads are assigned segments along the N dimension. Okay. With the knowledge of data layout, now let's talk about the problem of chain dot. So This problem refers to we want to use the result of the first dot as the input to the second dot. And which input to the second dot makes a difference here. So if we are talking about input B to the second dot, we are good to go because input B and output D have the same data layout. To put it another way, there's no need for redistribution of elements among threads. However, if we're talking about input A to the second dot, we have to go to LDS to rearrange the data among threads. So this is not good. So let's see how we can avoid this redistribution of the second case, which is what we have in flash attention. At software level, we swap the operands. And now you can see the elements from matrix A are passed to the MFA instruction as input B, and elements from matrix B are passed as input A. Okay, so because of the way how the hardware interprets elements from threads, now we are computing B transpose times A transpose. Mathematically, we got D transpose with MFMA output layout. Now is the interesting part. MFMA output layout on D matrix is the same as transposed MFMA output layout on D, because threads are held in the same elements. Okay, so in this way, the output is ready to be used as input to the second dot, and we achieve transposition without transposing anything in the hardware, so no overhead. Software pipelining, this is the tricky part. So we are developing a two-stage software pipeliner with one buffer in LDS and the other buffer in VGPR. So the compute always starts with data in LDS. It's never start with data in the buffer in VGPR. So the compute includes reading data from LDS and MFMA instructions. Okay, so we don't use the buffer in VGPR as a regular buffer because it is used as a stream buffer to wait for data from global memory. So while we perform compute for the current iteration of the loop, elements from the next iteration is being loaded from global memory into VGPR. And we always do the computation with data in LDS. So in this way, we achieve some kind of two-buffer software pipelining with only one buffer in LDS. So we save LDS space at the price of higher register pressure. Okay, so we also have implemented more optimizations on AMD GPU. So first, we try to keep Q-tensor. So in the context of flash attention forward kernel, we keep Q-tensor in register instead of loading it from global memory or LDS at every iteration of the loop. We also arrange warps vertically in the CTA so that we can do row reduction more efficiently. We reorder pointer arithmetic so that we can generate global load instructions with maximum vectorization length because the hardware is not doing a very good job on vectorization. We are also experimenting with this waves per EU attribute, which limits the number of registers to increase the occupancy. And we see great performance improvement when setting this attribute to 3 for flash attention forward kernel, which is weird, yeah. So because if you don't set it, it will be 2, so occupancy will be 2. But if we set it to 3, we have some register splitting, but we are increasing the occupancy, so we have better performance. Okay, performance. Gem performance. So this is kind of internal comparison of Triton and the Rock Blast on dense gems with different MNK values. So as you can see, we are still lagging behind Rock Blast, and we have larger gaps with small gems. And this is basically our to do work. We are optimizing on this kind of stuff all the time. And we have some to do optimizations. So first, we plan to store the result of MFMA instructions directly to global memory instead of going to LDS to rearrange the data. And also we plan to control the warp scheduling at finer granularity. Flash attention, forward kernel. So this is a comparison between MI250 and A100 for a flash attention forward kernel with 4 batches, 48 heads, head dimension equals to 64, and 0 dropout, and the causal equals to false. And with hardware specifications listed. So we got slightly better numbers compared to A100, and we also have some optimizations like we're trying to enable software pipelining for flash attention, and we also expect the performance, the jam optimizations will help flash attention forward kernel. That's it. Questions? Cool. No questions?
Hey, for all the flash attention optimizations you just talked about, are they require any changes to the tutorial or Triton up, or they are just compiler optimizations?
Good question. So the pointer arithmetic stuff requires changes in the Python level. This is something we are working on. We try to push everything to the backend compiler, and everything else is in the compiler stuff.
Questions, please raise your hand. Microphone is on.
Is there any intuition as to why it's so much slower than RockBlast for small MNK?
Yeah. I have some. So basically, when the MNK is small, we have the workload is small. So the workload is small, we have less parallelism, and our gem kernel is not optimized. So we do expect to high latency, like in an inter-warp manner. So when the workload is small, we don't have that many parallelism from neighboring warps. So it's worse. So after we can optimize gem kernel, we do expect we don't have to rely that heavily on inter-warp parallelism stuff. That's also explains why we're now performing better numbers on gem, but we got better numbers on flash attention. So yeah.
So RockBlast is like using a different algorithm there, or why is it so much higher?
So can you say it again?
But like the RockBlast is not having worse performance, right? Like, is it using a different approach, or why is it faster than Triton?
I think we are still working on, so our gem kernel is not optimized yet. We are still trying to learn something from RockBlast and grab their kind of optimizations and try in Triton. Because we have to tweak it in the Triton system and how to make it work in Triton system. So that's the work, that's the challenge here, basically. So it's not the same, they are different. And we are trying to catch up. Okay.
Thanks, Lixun and Jason. Next, we have Intel with the Intel XPU backend for Triton by Aiken. I'll